Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Dong Xin. He is a graduate student at the University of Illinois Urbana-Champaign, and he has been here with us for 2 summers, the last summer and the one before that, and we were very happy with his work, and we wanted him to bring him back for another visit, and here he is. Thanks.
Thank you. So good afternoon. Thanks for coming to the talk. Today I'm going to talk about our recent work on integrating OLAP and ranking. So here OLAP stands for On-Line Analytical Processing. It's a terminology in data warehousing. But if you are not familiar with that, it's okay. Don't care too much about these fancy words. The main idea is how offline materialization can help online query processing. And here we developed a method called ranking cube. Basically, we are looking for offline materializing method to efficiently process ranked queries. So this is the roadmap. We will first talk about motivation, and we will give a problem analysis, and we will talk about the basic framework of ranking cube and how we extend to high dimension data, and we'll discuss a little about our extensions, and finally the conclusion and future work. So recent years we have witnessed the data has been growing very fast, basically in 2 ways. So vertically, data has been growing from megabytes to gigabytes or even terabytes, and horizontally, data has been growing from a several dimension to 100 and 1,000 dimensions. So given this larger data set, the database system has some problems on query to do query processing. For example, a query may return too many results, and database system will return will keep producing those low quality results. It makes the query processing really inefficient, because at many times user only interested in a few but a high quality result. For example, this is my personal experience. I did some intern here. Before I came here, I will always look for an apartment to stay during the summer. So I input Seattle, I input 2 bedrooms in rent.com, and I got more than 700 results, and it's spread over almost 8 pages. And no one wants to click like 8 pages to look at each apartment. And there are similar search experience in when people search used cars on cars.com, search products on bizrate.com. But this situation reminds us a similar scenario in web search, where people input keywords and got millions of results, but people satisfied with web search. Why? Because they have ranking. Although there are millions of results, but people generally satisfied with the result on the 1st or 2nd pages. So how about we bring the similar idea to database search? For example, in this example, we will get so many 2-bedroom results, but I'm a student. I look for apartment which is cheaper. So my preference is that price over square feet as small as possible. So now we only look for, if we rank result according to this preference, we only look for top 10 or top 20 results. So let's look at the problem in more detail. We do have some hard selection criteria that I want to apartment in Seattle, I want 2-bedroom apartment, I want apartment to be furnished, and we have some soft ranking criteria. I do not know how cheap it is, but I want as cheap as possible. So this is the query I submitted in the previous slide, and someone else, they probably want to have different criteria. That means the cheaper apartment probably not that in good quality. They have some expected price like 1,000. They have some expected square feet like 800, and they have this kind of query. So, and they also want an apartment in LA. By the way, when I took this example in LA, they told me I was kidding. So with the square feet 800, there's no way that they only pay 1,000 in LA. But anyway, it actually shows that different people have different preference, even in different area. So this is another application scenario that we do some personalized search. And there are a lot of studies on how to learn user preference. This is not focus on this talk. But they can learn user preference by implicit user navigation behavior. They can learn the user preference by explicit user feedbacks. But to efficiently support this kind of preference learning, the system needs to handle this iteration quite well. For example, they will learn a ranking function in each iteration, and this selection will be very general, very ad hoc. And to make the whole system very efficient, the database system has to generate this top result very efficiently. So this is another kind of scenario that this method is greatly needed. So in general, let's look at the general formulation of a problem. We have a relation R. We have a set of selection dimensions, and we have a set of ranking dimensions or measure dimensions. And these two dimensions can be overlapped with each other. So our query is that we have not dimensional selections and also have ranking functions. So the assumption we have that given this ranking function, given a domain of the variables in the ranking function, we assume that the lower bound of our ranking function can be estimated. Here we assume we are looking for the minimum k. So the minimum value is best. So this is our query model. So the problem we are talking about here is how we can efficiently process rank queries with this dynamic ranking function and in high-dimensional data. So let's look at how previous solutions work on this problem. So basically, we have two constraints. One is the selection condition. One is the ranking function. So we can, of course, push this selection condition deeper into search, and we can also push this ranking criteria deeper into search. There are basically two ways. So these are summary of current solutions. There are actually more solutions I cannot put in the page, but there are some typical representative work. So we classify the method in two categories. One is there's no materialization. Everything is processed from scratch. So the only way we can do is table scan. So either there's only selection, there's only ranking, or they have both selection and ranking, they have to do table scan. So there are some work we call semi-materialization. The reason that I call semi-materialization is because we cannot get the result right away. We probably need some online computation. So for example, with selection only, we need to do index search. With ranking only, there are very fruitful research results on this. One influential work is the sort merge framework proposed by Fagan in IBM research. And there are selection and ranking, and we actually classify the previous work into three categories. One is the selection first. They only push selection deep into search. And one is ranking first. They only push ranking deep into search. And there's another work called ranking to selection, actually, which is developed by Solached and Nico. They transfer the ranking into range queries. And now our work is the ranking cube. So I put this selection and ranking here because the techniques used in this category, in this column, will also use their techniques. So this is quite a simple example. Let's look at how people do in selection first approach. And I actually had the details that just look at the problem in a logical level. So by selection first, they first select data that satisfy this selection condition. For example, in this small data set, they will first select this 3 data object. And then they rank these 3 objects by this ranking function, they output the best one. So the problem here is that no matter how they select this data, they're going to be select more because we only ask for top 1. And if the database is large, then this intermediate result is very large, and it's going to be some waste on the query processing. So the next one is the ranking first. Again, I will hide there the detail of how they do ranking, how they search best tuple, best object according to ranking function. But what they do is that they will first locate the best object which has the best ranking score, and then they go to next and they go to next. Unfortunately, all this data object does not satisfy this selection condition, and then finally they got this one. So obviously, this approach also has some disadvantage because they cannot push this selection and ranking together. So here's the largest work. I actually say I really like it, and they actually estimate the region for top result and then rewrite the ranking criteria to range selections. So it's very nice, but the problem is that especially when the dimension is very high, the estimation is difficult. So I'm not saying that our solution is smarter and our solution is better. Just we have some different assumptions. So our assumption is we would like to pay some cost for materialization. So previous methods they did their best under their configuration. So now we have different configuration. We want to do something new. We want to pay some cost for materialization. So our objective is to do efficient query processing. So in detail, we want to push this selection and ranking simultaneously into query processing. And we want to accept the dynamic ranking functions, and we also want to support the high dimension data. And what's the justification? We want to, first, before we develop a new algorithm, we want to know how much performance gain we can achieve. If there is small performance gain, there is no need to develop a new algorithm. So first of all, I will give a performance at the grounds. So we compare our method with 3 different methods mentioned in previous slides, and we can see that the method we developed here is the blue bar. Actually, the order of magnitude faster than the previous method. It's especially useful when the database is large. So this actually graph, this figure gives us a very good sign that there's large room for improvement. It's promising to go through this direction. So now we have discussed motivation. We have given a brief problem analysis, and now we'll go to the basic framework of ranking cube. So basically, rank cube did 2 things. We propose some materializing model to do some offline computation, and then we also use this model to do some online query processing. So we start from some ideal solution. How about if we pre-compute everything? Everything is pre-computed stored in database, and when there's a query, we just fetch it. So this is the best scenario we can do. So for example, given this query, like a city equal to LA, and this is the ranking function, and then we can group data by different attribute values. Actually, this is just a general data cube. They group data into different attribute values and according to different combination dimensions. And for this city equal to LA, then we have some ranking result. Top 1 ranking is T7, and this tuple according to this ranking function. And for example, for this selection condition that bedroom is equal to 3, we have another. It should be equal to 2. We have another top result as T2. Yes.
That you're making, are you assuming that the order by function is fixed?
Yeah, I will talk about this. So you will see this is unrealistic. So this solution is nice, is good, but it's unrealistic because we do not know the ranking function beforehand, and we also do not know how much space we have. Can we materialize every result for high dimension data? Then because the number of selection conditions grows exponentially with the number of dimensions. So let's look at if we sacrifice a little bit. So basically we have 2 constraints. One is the function dynamic, one is dimensions are high. So let's first focus on the dynamic function. Let's say the number of dimensions is low. We can materialize everything, and the function is dynamic. So instead of pre-compute the final result, we partition the data. For example, given this LA, we know these 3 data objects. And we can partition data in this way, according to price and square feet. So whenever there is a ranking function, we know where to search, because we know the bin boundaries, and given a function, we know which part is most promising for top score. We can go directly to that region to fetch data. And of course, similarly, we can for 2-bedroom, we can also give a data partition, like here. So what's the problem with this solution? This solution actually needs to partition data again and again for different selection conditions, and this is not a scalable solution. So the intuition of ranking cube is that we do not want to partition data again and again, repeatedly. We just have one data partition. And given a selection condition that basically filters data by this selection condition, and we have a sliced partition like this. So we do not repartition the data. We keep the original data partition as a template. We just put the data objects here in the original template. So in detail, I will show you a concrete example how we did this. So this is the original database, and given these 2 ranking dimensions, we'll partition data in this way. This is just for simplicity, we just use a very simple grid partition. We partition the price into 4 bins, and we partition square feet into 4 bins. And the intersection of them, we got 16 blocks. And then we assign the block ID for each block, and we know which tuple is in which block. Then we can group data by these selection dimensions, and again we have this different selection combination. Then for this LA, CT equal to LA, we know this is the sliced partition by filtering data given this selection condition. But what we do is that we do not need to store the partition information because there's only one single partition information which is stored here. So what we do is that we just summarize the data based on this partition information. So what we summarize is that we know there's only 2 blocks contains data that CT equal to LA, which is block 11 and block 5. So we have block level summarization is 11 and 15. And on data level, we know which data is exactly in that block. So in block 11, we know T6, T7 that satisfy this selection condition. And in block 15, we know T5 satisfy this block condition. So in this way, we just get rid of partition information. We just summarize data according to this partition information, according to this data partitioning. So given this pre-computed information, what we can do in query processing. So without ranking cube, given this ranking function, so price is 1,000 square feet, 800. We found the price here, we have 800 here. So we know this block is most promising for top answer. But unfortunately, this block does not contain any tuple, any data object satisfying this selection condition. But with this ranking cube tells us only block 11 and block 15 has this data satisfying this selection condition. So instead of starting search from here, we will start search from here. Because we know the bin boundaries of 11 and 15, we know which block is more promising for top answer. So in this way, we actually really simultaneously push ranking and selection together into query processing. So this is a more detailed execution trace. So the first step is where we retrieve a high-level measure for LA. This is block level. So we know block 11 and block 15. Then we estimate the lower bound score for block 11 and 15. So we know block 11 has this low bound score, block 15 has this low bound score. Then we retrieve block 11. That basically we retrieve data and their values. And we can retrieve low level measure for block 11. Basically we know that T6 and T7 are satisfying this selection condition. And we can evaluate the final score. The T6 is this score and T7 is this score. And we already found that T7 is better than the whole block 15. So we do not need to go to block 15. We actually already done. We can output the T7. It's the final result. So I have already shown the ranking cube in using a very simple partitioning method, which is a graded partition. But what I want to emphasize is that the ranking cube is just a framework. We do not rely on a particular partitioning method. Now here I will show some other partition methods. For example, the hierarchical partition method, I will use arbitrary as example. And this is the steps to build a ranking cube. The first one is that we will partition data, and second one we will group data, and the third one is that we want to integrate this data partition and group by. So the main idea is that instead of repartition data, we want to summarize data, and the summarized result we refer to as signatures. So this is arbitrary partition. So arbitrary partition data into hierarchical nest blocks, and the block corresponds to a node in the tree. For example, this is high level node corresponding to large blocks, and the low level node corresponding to small blocks. The structure in the tree corresponding to their relative position in the data partition. For example, this small block is contained by this large block, and this is the child of this N1. So the detail of how there are a lot of details how partition data uniformly or equally into different blocks. That's not important. The important thing is that we know this partition structure. We know data is partitioned this way, and how we can integrate it into ranking cube.
Are you exploiting the hierarchical nature of the partitions in any way? Mm-hmm. Or are you exploiting the hierarchical nature of the partitions, or it's independent of whether it's hierarchical or it's any arbitrary partition? Are you exploiting that N3 is actually a child of N1 and N4 is a child of N1? Are you exploiting that in any way in the query processing, or?
Yeah. I think for this particular partitioning, we do want to leverage this kind of property. When we search over their partitioning, we can do proving because we know this is child of the large node. So this is the way to provide proving. But I think for other partitioning, as soon as they have some proving method, we can use it. Yes.
So stepping up one level, it looks like what is important is the class of functions that you want to handle, right?
Yes.
If the class of function is just one function, the obvious partitioning is you just compute the values for all tuples based on that function and partition based on that. But if the class of function is any arbitrary function, I can't imagine any partitioning that can get you benefit. So implicitly, when you are looking at all these partitioning strategies, you have some class of function in mind, right? And what is that class of functions?
Well, I mentioned earlier that the assumption we have is that given the function, given the domain, we can estimate the lower bound. That's the assumption we have. So we can guarantee that the method works correctly.
It will work correctly, yeah. But for any class of functions, I suppose there is an optimal way of partitioning, right? So how do you pick whether you want to pick arbitrary partitioning versus grid? And it might be a function of the class of functions you want to handle. So
yes, right. For example, if the function is linear, we actually have some work in last year's VLDB. We exploit the geometry property of data, and we can partition data according to the geometry property because we know the function is linear. I think this partitioning method and the class functions is interesting, but it's orthogonal to this work, right? So we just want to integrate the partitioning method with the cube structure. But no matter what kind of function you use, no matter what kind of partition you use, it does not matter because as soon as they have the data partition, we can also incorporate it. I showed two different partitions. I just want to show that this is the general framework. We can support different partition method. Of course, partition is important according to different ranking function. Yeah. Okay. So again, given this arbitrary partitioning, how we can do how we can compute ranking cube. So again, this is the data, and we partition the data according to this ranking dimensions. And again, we can assign block ID instead of one single ID. We know they are the paths of the in the tree. So again, we can group data by selection dimensions, and we can compute a signature. So for example, when for city equal to LA, we can locate this 3 data object, and we know they are here in the tree structure. So when they are data here, then we put one here. So this signature corresponds to this tree structure. So whenever there's a 1, then we trace back to the root, and every node they pass through has 1. So every node that does not touch is 0. So if they are 0, then the whole subtree is truncated. So in this way, we use a bitmap tree to encode the data residence.
So these are only the tuples where city equals LA, is it?
Yes, there's only tuple. So actually, this corresponds to these 3 tuple, and this 3 tuple correspond to this 3 objects, and this 3 objects correspond to this cell. So this we call this structure as signature, and this signature is exactly what we stored in here.
So the signature is dependent on the specific partitioning strategy, is it?
But for this partition strategy, we use this kind of signature.
There's no generic signature scheme that you have, or is it? And because this is a hierarchical partitioning scheme, yeah, you can have this kind of a tree structure signature scheme.
Yes.
But if it's any arbitrary partitioning scheme, then you may not have this, right?
Yes, exactly. So the baseline is that we store the ID of tuple, data object. But this is kind of alternative ways that we can reduce some space. So using this signature, we can again prove such a space. For example, given this LA signature, given this bitmap tree, we know this region can be proved because we know there are no data in this region satisfying this selection condition. So without rank cube, we will search the whole tree, the whole overall region, and with rank cube, we will prove the shaded blocks. So here are some experimental results. So let's consider the optimal search scenario. So a block in our tree has been retrieved if it contains data that may have that may rank high. They also satisfy this selection condition. With this ranking cube, we can prove that we only retrieve the optimal number of data blocks, but we need to pay some cost. We need to retrieve the signature from disk because this signature can guide us search. So we want to show that this retrieving, this disk access, this overhead is small compared to the whole query processing. For example,
When you say optimal, are there any assumptions in the class of functions? Or can you say it's optimal for all ranking functions?
No, the class of function is that the lower bound of this function can only be estimated by the given region. We can estimate the lower bound of function.
That's the boundary.
Yeah.
So how tight do they have to be?
Does not matter. Soon we can estimate. And in the other way, the assumption is that without this boundary, you cannot estimate the function. So it's kind of this kind of assumption. So without ranking cube, for example, we will touch more than 1,000 this archie blocks, and with ranking cube, we can reduce the number of blocks in one order of magnitude, and the measure we call signature actually is for the orders of magnitude less. So in next slide I will show how we organize signature in disk, how we put them into blocks, because we actually the unit here is the number of blocks. So given one single signature, how we can partition them into blocks. So this is the next slide. So computer signature actually consists of three steps. The first is how we generate this signature. For example, given a selection condition, let's say if we traverse the R tree and we get data as a computer signature, that's not a scalable way because we need to traverse R tree again and again. So an alternative way is that we just traverse this R tree once and we output a path for each data object, and we store this in the data. We create a new dimension here. So given a selection condition, we can find the data objects and we can recover this tree structure. And given this binary tree structure, we can first rewrite it to a binary string, and then we can do bitmap compression. For example, the typical long length bitmap compression can be used here. So of course, when database is very large, then this bitmap, even if it is compressed, this could be very, very large, larger than a block size. So what we do is that we want to decompose the whole tree into small trees, and for each subtree, we guarantee that they fit into a data page. So in this way, we will retrieve data signature from high level to low level. In the beginning, we will retrieve from root, and when it is referenced, we will retrieve the subtree. If it is not referenced, we will keep it in disk. We will not retrieve it. So here is something about how we increment update this signature. For example, for R tree, if there is no node splitting, that means the structure of the data, the structure which does not change. For example, we just insert a T4 in this empty slot. Then what we need to do is very simple. We just update this signature for this particular data tuple. In some cases, they are more complicated that they insert a T2 here because they want to keep the partition balanced, and they do not have room here. They want to repartition this whole tree. For example, they repartition data in this way. So they create a new partition here, and T2 is here, and T3 is moved from this block. So in this way, there are more data changes their place, and we need to consider all the data that has changed, and we need to update all the signatures that are related. But the main idea here is that we only want to find the local updates, and we will only update the signature for those local updates. So now we have finished the basic framework of ranking cube. So far, do we have any questions? Okay. So next, I will talk about how we extend this framework to high dimension. By high dimension, we mean the high selection dimension and high ranking dimension. So we'll discuss how we handle these two different scenarios. So for high Boolean selection dimension, it's probably simpler, but for high ranking dimension, it's more complicated. So this is the basic factor of the curse of dimensionality. So when dimension is high, as I mentioned earlier, that we cannot pre-compute all selection conditions. And also, when dimension is high, when selection dimension is high, it's very difficult to partition them in one single partition. For example, we already know that the perfect dimension for R tree is 3 to 4 or 5. If we go higher, then partition performance is not that good. But what we observe from real application is that data may contain very high dimension, but the query only consists of low dimension. For example, in web search, the text dimension is very, very high, but typically people only input 2 or 3 keywords. So the query dimension is not that high. So our solution is that we only materialize low dimension only materialize low dimension signatures for selection dimension. And of course, we cannot cover every possible of combinations. And the problem is how we can assemble ad hoc measures online. So the other way is same, that we can only create low dimension partitions for ranking dimensions, and we can assemble ad hoc data partitions online. So this is for high selection dimension, this is a very simple solution. For example, we have 4 selection dimensions. One is city, one is the number of bedrooms, one is in which year the apartment is built, and whether the house is furnished. So if we consider all kinds of combinations, there are 2 to 4 of all 16 different dimension combinations. So if we do not have so much space, we're only able to afford some partial materialization. What we can do? So of course, one way is that we can exploit the query history. We can look at those frequent selections in query history, and we only materialize those frequently used selections. And the other way is that if we do not have that workload, we just use some atomic configuration. That means we only materialize only one-dimension selections. For example, we materialize selection for city, for bedroom, for year, and for furnished. So if the query comes that they want to ask for LA and 2 bedroom, we will retrieve the signature for LA, we will retrieve the signature for 2 bedroom, and we can do simply a bit and operation. So if they ask for LA or 2 bedroom, it's similar. We can do bit or operation. It's similar, same way. So now we are talking about how we handle high ranking dimension. So let's say we have very, very high ranking dimensions. So what we do is that we want to group ranking dimension with size G, and we will partition data for each group. For example, for this group, we will partition data into some hierarchical way, and for this 3 dimension, we will also partition data in this way. So the value of G depends on the different partitioning method. Typically for Arch, 3 to 4 is a normally used number of dimensions. So the problem is here. So given a query, it's possible that this ranking function consists of attributes which comes from different data partition. How can we handle this? So for example, we have price, we have square feet. Price is partitioned this way, and square feet is partitioned this way. And then we have ranking function, which consists of both price and square feet. And the price and square, there are no single partition consists of both price and square feet. So what we do is that we join these 2 data partition. So by joining, we join the root, and we join their leaves. So the number of joint states just the Cartesian product of the partitions from each part. So for each joint state, which is virtual, which is not pre-computed, we can get their boundary as a boundary from P and boundary from S. P stands for price, S from square feet. We can also get the result, the joint result, which basically is the intersection of the tuples from this block and this block. For example, this P1 has T1, T2, T3, and this S2 has T1, T4. Their intersection means the data object which appears in both. So this is only T1 here. So this is the structure of the joint space, and what we do is that how we can search over this joint space efficiently. So a straightforward search is very expensive. That we first materialize.
Does the join happen at query time or
at query time?
So can you take? I mean, only the nodes which are non-empty will be joined. Yeah, I guess.
Yes. So we only materialize the price and okay. So the straightforward search is that we join them, assemble the joint states first, then we search the joint state, which of course is expensive. So there are something smart we call the progress and select join. Basically, we observe 2 things. First, we want to identify which joint state has top score, and you want to assemble those joint states first. So the next one is select join. That we want to identify which joint state contains no empty result. That's just like you mentioned. We want to avoid generating joint states that are empty. So this is our recent work in SIG mode. So this is the first challenge on the complexity of join. So let's say we join price and square feet, and the number of children is the Cartesian product of the number of partitions in each part. So let's give a very simple calculation. If we use B tree to index price and use B tree to index square feet, and we have page size 4 KB, and the fan out of our node is around 200. So if we join 2 B tree nodes, then there will be 40K children. And if we join 3 B tree nodes, there will be 8 million children. So this number of children grows exponentially with the number of data partitions. So what we do for this case is that we do not want to join all these join states online at the same time. We want to only join the good state, the good join state. So we call this a progress join, and we actually develop method for 2 different cases. The first case is that, well, we have some very nice function. The function is monotone or convex. So given this function, we know which state is best because we can analyze the extreme point. For example, given this ranking function, we know the price around 1,000 and the price square feet around 800 is best for this ranking function. So in this case, we know that this block and this block combined the 2 is P2, S2 is the best state. So we will first look at this state without looking at the other state. So if this state, we join this state out, if like say there are not enough data, because we ask for top 10, then there are only 2 data here, then they are not enough. We need to look at other data, look at other join states. So what we do is that we just look for the neighboring states, because we have some nice property of these functions. It's monotone, it's all convex. So if this extreme state, and the next best is the neighborhood. So we just replace P2 with P1 and P3, or replace S2 as S1 and S3. So the next step we just look at this neighboring states, and then if there's not enough, then we continue to look at the neighboring states step by step.
Do you order within the neighbors, or all of them have to be fixed?
Yes. So exactly. So the assumption here, if we want to use this method, we are confined to B tree. We are not able to use R tree. So that means the data partition is fully ordered. So in R tree, the data partition is somewhat random, or we do not have fully ordered property. So we cannot use this property. So we call this a neighborhood search. Neighborhood search is only applied to grid partition or B tree partition, where the objects, the data partitions has some fully ordered property. Now let's look at a general case. We have general functions and we have general data partitions. For example, R tree, they are not fully ordered, and the function is not monotone, not convex. So what we can do? So this algorithm is somewhat similar to the sort merge framework. What we do is that we sort PI by this function. Then we couple PI with the whole region of S, and we sort SI by this function. That means we couple SI with the full region of P. So we know that this different block has different lower bound score.
F is the original ranking function?
Yeah, F is the original ranking function. So given these 2 blocks P and S, we can know the boundary on P and S. Then we can estimate the lower bound score. So similarly for PSI, we can also estimate the lower bound score. So we can sort PI and SI according to this score. So for example, for price, we can sort it this way: P2, P1, P3. And for square feet, we can sort it by S2, S3, S1. Depends on the estimated scores. So what we do is that we join P and SI progressively according to this list. For example, we first join P to S2, and then we can materialize this join state, and we can retrieve data, and then we can get the data out, and then we can compute the final result. And the good property is that we can look at the next best. So in this case, the next best is P1 and S3. So we look at the minimum of these 2, and this is 10,000. And then we already found a data which has best score 0. So we can stop, because everything coupled with P1 must have a score larger than this one, right? Because the possible score is that P2 coupled with any one of them, and the S3 coupled with any one of them. And we already know that S3 coupled with the whole region, the score is 10,000. And the P1 coupled with the whole region, the score is 40,000. So in this case, we can safely conclude that we already find the best state. So this my algorithm is similar to the sort merge framework, and we just use the seeing unseen framework to do proving. Now let's talk about the second challenge. How about how we handle empty joins?
One quick question in the previous slide. How do you get those orderings P2, P1, P3 just from a query? You already
Yeah,
know
given
the
the
list of
function,
orderings.
given this estimation, we order this P2, P1, P3 according to this lower bound score.
But the list of all partitions is already
This is done step by step. For this, here I show a very simple scenario that we have one level. But if there are multiple levels, when we join a two node, before we join two nodes, we know the boundary of the children. So when we join two nodes, then we have a children list, they have children list, and we can estimate. Yeah.
Oh, you do it the hierarchical.
Yeah. So this algorithm is executed at each time when we join two nodes. So as soon as we want to join two nodes, we need to do it. So there are more details on how we can incorporate this algorithm into the whole query framework. So the basic idea is that we call algorithm a double heap algorithm. So one heap is used on the global level to control the join state. And so for each join state, we have local heap to control the status of the join result. So there are some details in the algorithm. I just highlight from here. So the second challenge is how we can identify the empty joins. So, for example, if we join B trees on 1 million data, and we can because the data are exclusively distributed in different join states, so we can conclude that there are up to 1 million non-empty join leaf states. No matter how many join states here, there are only up to 1 million of them is non-empty, because data are exclusively distributed different data join states. So, for example, if each B tree has 5,000 leaf nodes, and we join two B trees, they are going to be 24 million join states, join leaf, and then we can see that we can conclude 96% of them are empty. And if we join three B trees, and they are actually 99% of them are empty. So this is a very serious problem because with a very high probability, we get a join state that's empty. So this problem is also applied on the sort merge framework in Fagan's algorithm. They do not use tree structure. They sort data sequentially, but they will join the data one by progressively, and they also have this problem because the join is empty. But they use some algorithm called random access to remedy this problem. But there are some details in our paper where we show that in index merging, when we join two tree structure data partitions, this random access does not work, does not help. Random access cannot help to early stopping.
Question?
Yes.
Do you think that if you have very large data sets, you would not end up with empty nodes, but rather you would end up with nodes that have very few data points in them? So you would not be able to prune them because they're empty. But
You are saying that if the database is larger, then there are less empty states?
well, if you have enough data, there'll be a bunch of nodes that are not empty, but they have very little data in them.
Well, I'm saying empty is that the join result is empty, not the origin data. The origin node is not empty.
Well, that's what I'm saying. Is that because if the distributions are wide enough, once you're looking effectively at the covariance matrix, right? And you're saying in the ideal scenario it's pretty diagonal, but in reality it's still going to have stuff all around. So you would still have non-empty nodes.
Yeah, we still have.
Like wouldn't you want to prioritize by node size?
Well, I'm saying that yes, we still have non-empty nodes, but the empty nodes, the probability of empty nodes is large. So when you join two data partitions, the number of join results is quadratic.
Well, you're placing assumptions on the way the data is distributed, right? The way that partitions are created.
I think that I mean when I say that up to 1 million non-empty join states, I actually does not care about the distribution. This is upper bound they have. This is upper bound they have for the non-empty states. Yeah. Okay. Yeah. So what we do for selective join is that similarly we use some idea in ranking cube. In ranking cube we integrate the selection and the ranking. Now we need to integrate the ranking and the ranking. So for example, for this data object, we know the price is in P1 partition and the square feet in S2 partition, and so far for all the other data objects. So what we do is that given this data partition, we can get a matrix here. So this matrix basically says which part is 0, which part is 1. 1 means their data, the join result of this P1 and S2 is not empty. And 0 means this join result is empty. So given this one, we can follow compressed by Bloom filter or some other compression method, and then we store this one for each join state in the disk. So this we expect the size of this matrix can be fitted in a data page. If it's larger than data page, we will compress it by Bloom filter. But of course, there are other nice solutions, and I will mention it in the future work. So the way we avoid this empty state is that we just check this join signature, and before we go to before we start to join them out. So this is the overall materializing cost. So we would like to see how much space we used to store this ranking cube. For example, in this synthetic data set, we have 100 Boolean dimensions, we have 12 ranking dimensions, and we build 4 data partitions, each have 3 ranking dimensions, and we construct atomic signatures and all two-way join signatures. And this is the size we used. This blue bar is the original database size, and this is the fourth bar is the space used by ranking cube, and this yellow bar is the space used by arch data partition. So we can see the size actually is equivalent to the original database size. So we actually control the materialized cost quite well. So this is the query performance. We vary the number of selection conditions. We also vary the number of ranking attributes. And this figure shows that we only materialize the atomic selection dimensions. And when we get 3 Boolean products, and the cost is only increased a little bit because we already show that the cost for retrieving these signatures is low. And here we show that when we vary the number of attributes, number of ranking attributes, we still can do pretty well. But of course, when the attributes is larger than we need to jump. Yes.
What is the data set you use?
What synthetic data?
Sorry.
Synthetic data. We generate data.
Oh, okay, got it.
It's not real data. But we want to study the property of the data. We have free control of the data.
What are the attributes? What are the attributes in the synthetic data?
Oh, we have 100 Boolean attributes. We have 12 ranking attributes.
And ranking ones are just continuous. They're randomly distributed. Random.
It's random. Yes.
Is it just uniform randomly across every dimension, or is there some correlation?
Oh, there's no correlation. It's random. So yes. So now we discuss a few extensions. So the first extension is that how about this selection condition is numerical. So we have numerical attributes. For example, we also can put price as a selection condition. We want to select an apartment with a price between 500 and 1,000. So there are 2 ways we can handle this. The first one, we can discretize the numerical attributes into different bin blocks, and we can transfer this range selection to equal selections. And the other way is that we can treat this range selection as a special ranking function. For example, if the price satisfies this constraint, then we compute the result. If not, then we just out to 0. So this is the way we integrate this selection into the ranking. So there are other extensions that, given this framework, instead of this topic query, we can handle other queries like skyline query, nearest neighbor query, or convex Hall queries. So I use a skyline query as example. For the skyline is that if A dominates B, because we call A dominated B because A has larger square feet and A has lower price. So A is better in any way. So we call A, B is dominated. So if a data object is not dominated by any other type, it's a skyline. So how how to handle these skyline queries. So this is the original framework for process top K queries. The two most important part is that we keep the top current result, and we look at top K with the next candidate block. So this is the way we can do early proving. We can do early termination. So when we process skyline query, what we do is just replace these two lines. For example, we do not keep the top K result. Instead, we keep the current skyline list. So instead of compare this top K with the next block, we actually bring this next block and we check with the previous skylines to see whether it's dominated or not. So this, I'm not going to detail this query processing. I just want to show that the method, the framework is general and that can handle other preference queries, not confined to top K query. So now I'm going to talk about conclusion and future work. Okay. So conclusion that we identify problems that the data is growing very fast and the ranking is effective to explore data. And we propose a rank cube which supports high dimension data, which facilitates dynamic ranking functions, and the performance is good. And for future work, so the short term for ranking cube, the next step is that we want to support ranked aggregates. We want to support very high ranking dimensions. Here we compute the join signature, which basically is the pairwise two-way join result. So when the ranking dimension is really, really high, then this complexity grows quadratically. It's not a very scalable solution. So how we can support a very high ranking dimension is an interesting and important problem. And we will leverage the workload information for smart data partition. So I have working on data cube, which provides the high level summarization because like a sum average. And then we also work on ranking cube, which provide low level feature data set, top K data object. So it's nice. It would be nice if we can provide something in the middle. For example, how we can do data summarization, how we can do clustering given this selection condition. And also there's some works that given this selection condition, how we can do regression and how we can do classification. I think Bijon and Raghu has a work called prediction cube. They basically build a classification model in the data cube environment. And there's another work done by our group we call regression cube. They basically build a regression model in different cells in data cube. So I'm interested in explore non-relation data. This is related to some intern work here. For example, we can explore structured information like entity text, because entity has very special, very good property, like entity has some hierarchical structure, and we can explore that. And we can explore new query interface. For example, instead of ranked entities, we can rank the paths between entities. Let's say two people, how they are connected. I think this is probably an interesting problem in social network analysis, maybe in CMT, like how you find the conflict of interest. And of course, we want to explore data by both database operators and the search criteria. So finally, I will briefly mention other work in my PhD study. So I have been working on data warehousing, build algorithms for cube computation. I worked on ranking query processing. And so this work is done with causal ranking here. And this is the work we exploit geometric properties of data. We build an indexing called robust indexing for linear ranked functions. And this is ranking cube work. And I also did some work in data mining, basically on pattern analysis. The major motivation is that the whole data mining community has been working for like 10 years to develop an efficient algorithm for pattern mining. There are probably more than 100 algorithms to mine frequent patterns, but there are very little work on how to use or how to interpret those frequent patterns for real data mining applications. So we did some preliminary work on this. Basically, we identify how to compress patterns because there are so many patterns. Sometimes that when we give a data mining algorithm a data set, they will mine pattern whose size is larger than the data set. So how we can compress patterns, and how we can extract important top K patterns, and how we can annotate patterns with the semantic structure information. So this is kind of work I have been working in UIOC. And thank you.
any of the real data sets where the number of numeric dimensions or the ID dimensions is high?
Well, we actually do not try in very high dimension data. But now the engine, the query engine is used in another project. We have a project called Datascope. It's an NSF project. It's like to visualize the data, the relation data, and in map we can draw down, we can roll up, and this top key query is important to show the contents of each cell. So we are currently using this ranking cube engine in that
What are the
project.
ranking dimensions in that scenario?
Ranking dimension, like we use DB architecture as a demo. So ranking dimension could be the number of papers or something like this, but not very, very high. Yeah.
Thank you.
Thank you.